In this video, we're going to look at the intermediate value theorem, the extreme value theorem, and the sandwich theorem. So let's start off with the intermediate value theorem, and this we're going to oftentimes just abbreviate as IVT. And what this says is the following. If some function f of x is continuous on the closed interval AB, then f of x takes on every value from, or let's say not from, let's say between f of a and f of b. And before I go to an example, let's look at a little graphical representation of what's happening. So we have this. We have some function that goes from a to b, and I know that f of a is here, f of b is here, so I'm just making this example up. Now, regardless of how I connect these points, okay, so I sort of connect them with a straight line or almost a straight line. I could connect them with a parabola. I could connect them with some weird linear change on a trig function. But no matter how I connect these points, the f function is going to have to hit everything between this f of a and f of b, because there's no way for it to have a jump that would cause it to be not continuous there. So I have to somehow hit everything. Now notice, if I do something like this parabola, it doesn't just hit values between here, because you can see over here, I can be outside of f of b and f of a in this case, but I do have to get everything that is between them. So let's look at an example. What does the intermediate value theorem tell us about f of x equal to x squared minus 2x plus 4 from x equals negative 1 to x equals 2? So what it tells us is the following. First off, I know that this is a polynomial, which means that it is continuous everywhere, and in our case, from x equals negative 1 to x equals 2. Second piece of information I need is what is f of negative 1 and f of 2. So negative 1 squared is 1. Negative 2 times negative 1 is 2. 1 plus 2 plus 4 gives me 7. 2 squared is 4. Negative 2 times 2 is negative 4. Plus 4 is 4. And so I have this from 7 to 4. And so what the intermediate value theorem tells me is the following. Let me write this out. The IVT states that f of x equals, let's say that, takes on every value in the closed interval 4 to 7, the output values, for some x in the open interval, I guess the closed interval, negative 1, 1. Or negative 1, 2. Okay, and what I can do is this. I can say, okay, so when does it equal 5? Because 5 is in this interval. So f of x equals 5. I can actually solve this off and get 5 equals x squared minus 2x plus 4. I can solve this by subtracting 5. I get 0 equals x squared minus 2x minus 1. I can put this into the quadratic formula. I get 2 plus or minus square root of 4 minus, so b squared, so 4 minus 4 times 1 times negative 1, so it's going to be plus 4 all over 2, which is going to be 2 plus or minus 2 root 2 over 2, which is going to be 1 plus or minus root 2. And in here, 1 minus root 2 happens to be inside this interval that we're looking at, and when I put this into the function, I will get the output of 5. So graphically, here's the function, and we are considering this from negative 1 up to, or sorry, negative 1 up to 2. So I can put the points we had were negative 1, 7, and 2, 4. And I can restrict this to those points. So if x is greater than or equal to negative 1, and if x is less than or equal to 2, there we go. And you can see, all right, here's what the function actually looks like on that interval, and I do hit every value from 7 down to 4. I get some extra, but I hit every value in there. All right. Extreme value theorem. So the extreme value theorem, or what we will commonly refer to as EVT, basically states that if some function f of x is continuous on a closed interval a to b, then f of x has a maximum value and a minimum value in that interval. And graphically, let's see what that entails again. So I have this, I'll draw a different one. Okay, so this one's increasing. There's A, there's B, this is f of A, this up here is f of B. And if I were to just connect these points up, then in this interval, the minimum value happens at A over here, the maximum value happens at B. If I did something like this, the minimum still happens at A, the maximum now happens over here. And you can see, as long as these are continuous, there's no way to sort of break it. I can't go off to an infinity, which would cause it to not have any maximum. The closed interval is important, because if this were an open interval, then I could have this case where I approach a maximum value, but I don't actually have it in there, so it would not have a maximum. It would just approach something. It would have an upper bound, but not a maximum. But that's the idea. So let's see an example of this. So what does the extreme value theorem tell us about this? Well, the EVT basically states that f of x must have a max and a minimum somewhere in this interval, negative 1, 2. It does not tell me where they are, and it states this because f of x is the same polynomial, which has to be continuous on this interval. Now that's all the EVT tells me. I can actually find those by doing some work. So this will lead into some things we'll see later, but the extreme values for this type of function, for a parabola, can only happen one of two ways. will either happen at the vertex or at the endpoints of this. And so we know the endpoints gave us x equals -1 and x equals 2. If I go through and try to figure out what this vertex is, I know I have that formula -b over 2a to find the x value, which means that we have 2 over 2 times 1, which is 1, so x equals 1 will be where the axis of symmetry is. It'll tell me where the vertex is. And so I can just find these 3 points, find these 3 values. So f of 1 will equal 1 minus 2 plus 4, which is 3. F of -1 will equal 1 plus 2 plus 4, that's 7. And f of 2, we already figured out, but I'll go through it again. 2 squared is 4, minus 4 is 0, plus 4 is 4. And so you see, okay, this one was the lowest, this one was the highest. I can say without looking at the graph that f of x has a maximum value of 7. The value of the function is the output. And I like to be very specific at x equals -1, and f of x has a minimum value of, the lowest value is 3, at x equals +1. And looking at that graph, you can see, yeah, at -1 we were up here at 7. At +1 we were at this lowest point at 3. I don't want to come back up here. This one isn't the lowest up here. Alright, last theorem is the sandwich theorem. The tastiest theorem in calculus. So in here, all this says is the following. If we have 3 functions, f of x, and this is the function that we sort of care about. This is the one we'll be given. And oftentimes we'll have to consider 2 other functions, g of x and h of x, so that g of x is less than or equal to f of x is less than or equal to h of x on some open interval a, b. And I'm going to add something in here that it's important, but just sort of confuses matters. But I'll add it in here to get this on here. Except for possibly at a point C in that interval. Okay, so maybe not at that point. And if the limit as x approaches C of g of x is equal to the limit as x approaches C of h of x is equal to some value L, then the limit as x approaches C of f of x must also equal L. Here's the idea. We have a sandwich. G and H are the pieces of bread on the outside of the sandwich. Okay? So we have G, we have H, and F is the filling somewhere inside. Okay? I guess G is the lower, so this is G, this is H, and F is this inside. If at some point we squeeze the sandwich enough so that the lower function and the upper function have the same limit, and that would mean they sort of approach the same thing, and the filling is stuck inside there somehow, then you can see the filling actually has to approach the same thing. Think of it like a peanut butter sandwich with 2 pieces of bread. You squeeze the bread, you know exactly where the peanut butter is. So let's see an example. So here's the idea. Now, I'll do it with the functions, but there is a much easier way to get the value of this. I'll show that afterwards. So here's the idea. I see this function here, and I think, okay, x squared, x, and negative 2 behave pretty nicely. This sine of 1 over x is what causes the problem. But the lowest value of sine is negative 1. So I know that on the low end, the worst this could be is x squared times negative 1. So I have a negative x squared plus x minus 2. On the high end, h of x, the biggest that sine can be is 1, so the biggest this function can be is x squared plus x minus 2. And f is somewhere stuck in the middle. The limit as x approaches 0 of g of x is going to equal, well, this is approaching 0, this is approaching 0, that's negative 2, negative 2. The limit as x approaches 0 of h of x, well, that's approaching 0, that's approaching 0, is also negative 2, and therefore, the limit as x approaches 0 of x squared sine of 1 over x plus x minus 2 must also equal negative 2. Before I show the easier way to get this, let me look at it graphically. So here's our old graph, get rid of this stuff. Here is our function. Okay. Let me zoom in a little bit so we can see what happens. So it doesn't get interesting except right around 0. I'm going to zoom in, and I'm going to, let me do this, let's see, zoom in a bunch. Okay. So you can see it gets sort of wiggly here. Alright. But it clearly looks like it's approaching negative 2. It actually has a hole there. So the way I can say, okay, even though there's this hole here, h of x is always below, k of x is always above, and so, let me zoom back out, you can see, alright, the red curve is always stuck between the blue and the orange curve. I know the blue and the orange curve meet here because they eliminate that sine of 1 over x, and so that limit had to be negative 2. Now, there's a much easier way to deal with this, and here's the way, okay? So if you have a product limit of two things multiplied together, one is approaching 0 and the other one is bounded, the net limit will have to equal 0. What I mean by bounded is it has a minimum and a maximum that's stuck between. In this function, x squared goes to 0, it's approaching 0, and sine is stuck between negative 1 and 1. Those are the minimum and maximum respectively of sine. So 0 times something stuck between negative 1 and 1 will approach 0, regardless of how crazy this 1 over x makes things. So this portion here approaches 0. X, as x approaches 0, also approaches 0. And the negative 2 just hangs out there, and so we can get there without coming up with the function, just realizing that this 0 collapses this thing down to 0. Alright, feel free to comment below if you have any questions.